So I just wanted to make a quick video showing off a technique that you can use that makes your rigs a little bit faster and makes your outliner more organized. There are a couple nodes in Maya that give you outputs in world space only. For example, here I have a curve, and this locator is attached to the curve using a motion path, as you can see here in the node editor. And the outputs of all coordinates and rotate that comes from the motion path only works in world space. If I were to take this do not touch group and move it around, you can see that the locator is no longer attached to the curve because it's getting those same inputs as before, but now we have this extra transform that's on the do not touch group above it. So ordinarily, the way that you would combat that is put all your locators that are taking outputs from those sorts of nodes and put them in a do not touch group that has inherit transforms off. So that if I were to move the rig around, this do not touch group does not inherit those transforms from the parent above it. However, what that means for your actual rig is that you are going from the curve to a motion path to the locator, and then from the locator to a buffer group to the control, so that you can get this sort of behavior of moving the curve to move the locator to this control and then be able to offset using it. And then finally we have another parent constraint from the control to the joint. So the technique that I'm going to show you allows you to get rid of this locator, this do not touch group, and also this parent constraint. So let's get started. So before you can use this technique, you need to understand how matrices work in Maya, at least a little bit. I would recommend reading this article on keybonematara.com because there's two diagrams in here that basically explain what I'm going to be talking about in this video. This first diagram right here shows you that if you multiply the local matrix of an object, like locator 1, by its parent, and then its parent, and then its parent, you wind up with the world matrix of that specific object. I have another post that kind of goes into more detail about matrices in Maya. If you just want to know enough to use matrices, this article is good, but if you want to have a deeper understanding of it, I would recommend going back and looking at some of those other resources as well. The second diagram is down here. And this one looks a little bit confusing, but basically you could ignore this right half for the most part. Basically, it's the same as before. We have a local matrix for the object, but instead of multiplying by the parent matrix and then the parent matrix to get the world matrix, we can actually multiply by a single matrix called parent matrix. And you can actually see that in Maya right here. Every object has a parent matrix under its transform node. So if you have some understanding of what those diagrams mean, we can get started. The first thing that we need to do is turn this motion path node into a world matrix. So I'm going to create a node called compose matrix by hitting tab and typing that in. And if this doesn't show up as an option when you hit tab, you don't have your matrix plugin turned on. So we just need to go up to Windows, Settings and Preferences, Plugin Manager, and come down here to matrixnodes.mll and hit loaded. So what the compose matrix does is it takes translate, rotate, scale inputs and gives us a matrix as the output. So I'll come in here to the connection editor, load in the motion path on the left, and we can go from rotate to input rotate and all coordinates to input translate. I don't know why they decided to use the name all coordinates for the motion path node, but this is essentially an output translate attribute. So now we have the world matrix that an object would have if we were to take these translate and rotate coordinate transforms and plug them in as the translate and rotate attributes. So now what we need to do is turn this world matrix into a local matrix. We basically have to say what object would have the same world matrix as this one, but have a parent that isn't just the Maya scene. So in order to do that, we can look back at that diagram. You can see here that the local matrix of an object, which is what we want, is if we multiply it by the parent matrix, it gives us the world matrix. But we need to go in the reverse order. We have the world matrix, and we want to get to the local matrix. So you might be thinking, we can divide by the parent matrix. And you're kind of right. But when it comes to matrices, it isn't called dividing, it's called multiplying by the inverse. So what we need to do is take this world matrix and multiply it by the parent inverse matrix of the control buffer group. So I'll create a mult matrix node by hitting tab and typing that in. And we will take this output matrix, plug it in as matrix in, and we will take parent inverse matrix off of the group and plug it in as the second one. And now we've multiplied those two together, and the resulting matrix is the local matrix that would get us the same transforms as this locator had originally. So in order to go from this matrix to actual translate and rotate attributes that we can plug into the group, what we need to do is create a decompose matrix node. It's basically the opposite of the compose matrix node. So we'll take the matrix sum, which is the result of multiplying those two matrices together, plug it in, and then take the rotate and take the the translate, and plug it in. And you can see that it is right over here. And now it doesn't look exactly the way it did before because of this. This locator has this orientation, and this circle has the same orientation because it was up in the y-axis. If we wanted to change that, all we would need to do is come back over to the motion path and change those settings. So I'll have the y-axis be up, and I'll have the front axis be x. And so now it looks the way that it did before. So now that we have all that set up, we no longer need this locator or this do not touch group. Because now, instead of using a parent constraint on this control buffer group, we've created a series of nodes that basically gives us a local space motion path constraint. Not only is this system a little bit faster, but it is also a lot nicer to look at here in the outliner, because we don't need an extra do not touch group and we don't need that extra parent constraint. I'm going to do a second setup that uses a follicle or a point on surface info node instead of a motion path, so that you can see this process in another case. So first things first, I will create a surface. And then ordinarily, we would put a follicle on it, and then we would need to parent constraint something to that follicle in order to attach it, because this follicle only works in world space. See, if I put a parent above it and move that parent away, the follicle is no longer attached to the surface. But what we want is something that stays attached no matter what the parent is doing. So I'm going to create a locator, and I will color it so it's a little bit easier to see. And we will set this up so that it is attached to the surface, and we will also put it under a control here to show that it works. So let's bring the locator and the NURBS plane into the node editor. So the first thing that we're going to need to do is create a matrix. I'm going to create a point on surface info node. And we are going to take the world space attribute of the plane and plug it in. So the outputs of this node are several vectors. So we have like a position vector, we have a normal vector, which goes straight up, and then we have tangent, u, and v vectors. And then I'm going to turn on the local rotation axis so we can see if we're doing the right thing throughout the process. So you might not remember this from when you took pre-calc, I guess, or maybe you took a physics class, but matrices are essentially rows of vectors. So what we can do is we can take the normal vector and one of the tangent vectors and plug it into a node to create a matrix. So the node that we need to use is a 4x4 matrix node. So I'm going to create that by hitting tab and typing it in, and then I'm going to bring them both into the connection editor. So this looks very confusing because these don't really represent anything that you're familiar with. But I'm going to go into a matrix here on a decompose matrix node, and you can see that it is a 4x4 matrix. It's 4 across and 4 down. So basically what this row, this top row represents is the vector that the x-axis is pointing in. So in this case, it's pointing in the x-axis. So the vector is 1, 0, 0. The second one is the vector of the y-axis. The third one is the vector of the z-axis. And this bottom row is the translation. So the x translation, the y translation, and the z translation. And these are all local translations. So what these attributes on the 4x4 matrix represent are all of these, but just in a weird naming scheme. So in 0, 0 is here, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, and so on. So what we need to do is take the normal vector, the one that's pointing straight out from over the surface, and use it as the y-axis vector of this matrix. So that means we are going to be going from normal x to 1, because it's the second row, because it's the y-axis, and the first item, so in 1, 0, and then in 1, 1, and in 1, 2. Now the second thing that we need to do is plug in something for either the x-axis or the z-axis. And if you've used an aim constraint, you might be familiar with the idea of an aim axis and an up axis. Basically, the way that a 4x4 matrix works is the x-axis is always the primary or the aim axis, and the y-axis is always the secondary or up axis. So what we're going to do is we're going to plug in tangent u or tangent v as the first row in the 4x4 matrix. I can never remember whether it's u or v, and sometimes it can depend because you could create your surface in either direction. So let's look at it like this. Let's try tangent u first. So we'll go tangent u as the first row. And everything looks the same. And that is indeed an x-axis vector. You could use the normalized tangent u, in which case this 9 would become a 1. It would just normalize the vector, so it has a magnitude of 1, but it doesn't matter in this case. So now what we need to do is turn this matrix into translate and rotate transforms that we can plug into this locator. And as before, we're going to use a decompose matrix node. So we'll take the output matrix that we created in this node, plug it in here, and then take the rotate and translate. So now it is attached to the surface, just like we wanted. But we still have that issue of moving the parent, causing the locator to detach from the surface. So before we can turn it into translate and rotate, we need to, again, multiply it by the parent inverse matrix. So let's take the output here, plug it in, take the parent inverse matrix, plug it in, take the matrix sum, and use it as the new input matrix of the decomposed matrix node. And you can see that nothing changed, but if I were to take that control that's above it, it no longer has any effect on this locator because all of its transforms are being compensated by multiplying by the parent inverse matrix. Now, looking at this node network, you might think that we have a cycle of sorts going on because we have translates going into here and then a parent inverse matrix going into here, and it kind of cycles around, at least by looking at the way the arrows point. But because the parent inverse matrix is not affected by anything you do on this locator, it's only affected by things that you do in the hierarchy above it, this is not actually a cycle, even though it looks cyclical in the node editor.